there's been evidence of a past wetter environment. Adrian Jones here, I remember coming out to me at a conference, excitedly telling me all about it, and I kind of thought, that's really interesting, but I was very skeptical because in my mind, Venus had always been dry. It just never had water in the first place. I didn't believe it had lost its oceans. I just thought it never had them. And that was the reaction that they got. The Venus community was quite closed, shall we say, to new ideas. It was dominated by certain geophysicists. But actually, funnily enough, Mike Warner said to me when I was telling him about this, he said, never underestimate Adrian Jones. 90% of what he says may be wrong, but the 10% is pure genius. So I sort of had that in the back of my mind, actually. And another colleague of mine, Dave Waltham here, who's just retired from Royal Holloway, I've known for many, many years before I came to Royal Holloway. And Veronica Bray, who was a student originally at UCL and came to Imperial when I was there. We worked on these sorts of channels, and I had the idea that the atmosphere is like an ocean. So we looked at modelling these canali as particulate currents as in the atmosphere. But actually, it's really hard. You can make it work, but it's really hard. It's much easier if they are actually in oceans. So these are submarine. These fit submarine channels really well. But nobody listens to Brits because it's a community that's dominated by American scientists. So it took this chap, Michael Way, who was a really lovely guy from New York, to do some modelling essentially about exoplanets, but essentially the question being, if you put Earth where Venus is, do you get Venus? And the models say, no, you don't. There's something else going on. It's not just the Goldilocks problem. It's not just that Venus is too close to the sun. Venus, if it had oceans today, would have oceans today. I know that's an oxymoron, but they wouldn't lose them under Earth-like conditions. So something happened for either to have never had oceans or to have lost them. And then I realized I didn't have a photo of Eloise, so I put one in here because the other places I've given this talk, she's been there with her poster or giving her talk herself. But anyway, this Eloise was a undergraduate student at Royal Holloway, and in her first year summer said, I'm bored, I'd like to do something interesting. Can you give me something to work on? I said, go away and look at Venus. There's lots of interesting things to look at. Go and look at the planes because I think you'll find out a lot. And I was expecting her to look at the canali and things like that, which she did. But she came across these things, polygonal fractures, lots and lots and lots of polygonal fractures. And so the following year, she had various health issues, so she couldn't go physical mapping, so she went digital mapping on Venus, and she mapped out these polygonal terrains on the surface, and she grouped them into two main groups, but 3 categories in each. So the truly sort of polygonal ones at various scales and slightly more ordered parallelogram type ones. But the really interesting thing about these polygonal fractures is their size. They're several kilometers across. They range down to the resolution limit, which is about 100 meters, but they go up to several kilometers across. And she looked at a whole series of analogues, and the only model that had been put forward at that point was global resurfacing, big thick lava flows cool down and crack into polygons. They don't do that. They crack into polygons that are this big, or maybe this big, but they don't crack into polygons that are kilometers across. And there are a number of ways in which you can make these polygons other than that, but they are all sedimentary. And the only way to make really big polygons is underwater, in fact, in deep marine sediments. And they're known around the world. In fact, Joe Cartwright, who I know was at Imperial and then Cardiff and Oxford and all around, was one of the key people behind finding out about polygonal fault systems from seismic data in basins on continental margins and other places. And it's not really fully understood how they form as such, but essentially it's a dewatering process. As the sediment load piles up, the water comes out and the clays shrink, and you generate these fractures, which become faults, which propagate up towards the surface. They don't quite make it to the surface usually, but sometimes they do. These are some in the Caribbean, and they make these furrows on the seabed. And these look just like the polygonal fractures we see on Venus. I'm not going to quiz you. Eloise did a quiz where she put 2 pictures up and said which one's Venus, and about 3 people got it right. It's pretty hard to tell them apart. What we can see also are that the smaller fractures, the smaller polygons, could be desiccation, they could be salt. There's a number of things they could be. So if Venus lost its oceans, it would then desiccate and generate salt flats that would reflect this larger polygonal structure, but with many, many smaller polygons. And this is an example from Lake Natron in Tanzania, in both radar and optical. Something else that then starts to fit into place is that the lowlands of Venus have wrinkle ridges on them, these funny small inversion type structures. And they're thought really to have been inversion structures in lava flows, but it's really hard to make them because they're strong materials, lavas. And these wrinkle ridges reflect gradients of fractions of a degree on slope. But you can make them if they're on salt. So that we think there's something like these salt walls and salt anticlines as the salt from the evaporates from losing the oceans, basically move down slope into the basins, and they occur in all the deeper parts of the lowlands. And in fact, actually, if you work it out, if the area they cover elevation-wise represents the hypersaline ocean, and you dilute that ocean to terrestrial levels, terrestrial salinity, then about 90% of the surface of Venus is covered in oceans about 1 to 1.5 kilometers deep. And those oceans include all the features, cover the areas where all the features that we see related to oceans occur. So these are all the polygonal fracture systems. These are the big long canali in the deep marine basins. These are the wrinkle ridges on the surface. And the continental areas stay high and dry away from it. And the nearest analogue we have really is the Messinian salinity crisis. And this picture came out just before we submitted this for publication. So this is one of these is Cyprus, and this is the Eastern Mediterranean. You can see these hypersaline basins here, still with the briny water in it. All the polygonal fractures are all out here. They're not really showing on this image, but it's picture, but they're out there. We can see all the kinds of features that we see on Venus. So it does really look like Venus lost its oceans. The question is when? And this is when it gets really interesting and quite exciting. So go back to these craters. These craters must have formed after the oceans were gone. And if we add them all up, all these bright floor craters where they are, we can get an age at which the oceans must have been gone by. But the other craters, they're much more interesting than just dark floors. Look at this one. This one's got a backwash into it of sediment. It's got sediment all the way around the peak area here. And the ejecta flows like a fluid away. This isn't impact melt, this is ejecta. And there's no blockiness to it, or very few blocks. It's all gloopy. So this is, I think, an impact that hit the sea. So this is a crater that formed when Venus had oceans. And then, we've got ones in between, the intermediate ones, during that interval. And there are 2 different things we can do. We can add up the number of different types of craters and get a date. And we can also look at the crater distribution, size, diameter distribution. And both those things point to the same age. And they point to an age of 309 million years. That's when Venus lost its oceans. Don't know how quickly it lost its oceans, but they were definitely gone by 211. And they were definitely there 442 million years ago. So we go back to the Ordovician, Venus had oceans, looked just like Earth. We go to the Permian, really nasty on Venus. I think it was bad here. It was really bad on Venus. So we can picture this. Venus with oceans in the Devonian. So you can imagine fish, plants on the land. I mean, I don't know if there were, but it's entirely plausible. And then it all goes wrong. The oceans start to disappear. We have hypersaline seas in the end of Carboniferous and towards the Permian, until by the Permian, Triassic, dead, gone. And those old blue areas that nothing's happened to, we can see the oceans. This is what I think is really telling. So I was talking through this with a sedimentologist at Holloway one day, and he said, well, that's a wave cut platform, and these are cliffs. And these are streamlined islands where the currents have been flowing along the floor. And look, this is the canale channel coming out, or actually maybe a fluvial channel. These are drainage channels cutting down, and we actually worked with people in Canada and published on these channels being flash flood deposits as the oceans came to an end. And yeah, put that into kind of 3D. You see, you could be walking on a beach with the tide going out. This is just draining away. Really quite evocative. And yeah, so one of my friends said, you should ask AI to show you what it looked like. Absolute rubbish, really rubbish. So instead I went to Wales. I think this is probably the best image of what evaporating oceans might look like on an orange planet. Yeah, strange. I found it quite sort of harrowing, actually, thinking about a whole planet sterilizing itself. I think that's quite a profound problem to come across. It's one thing to say there were bacteria on Mars 3 billion years ago and it didn't last. It's quite another thing to say there were fish 300 million years ago and then it got cooked.